Hello class, this is CSE-5250, sections 2 and 60, week 15, spring 2025. Alright, we are now at your last assignment for the entire quarter. The entire semester. And that is your MPI benchmarking project. I said we would have an assignment 3, but due to technical difficulties with trying to get it to work and having it in a understandable format, I instead opted for an alternate assignment that's basically your assignment 3 and benchmarking project combined. So, part 1 of this assignment is to write a pi estimating program in two ways. The first one is just your non-parallelized serial implementation of this pi estimating program, and then parallelizing it using MPI. So I have detailed instructions on how to do that, all in here. Once you have verified it to work, because with MPI programs, it doesn't matter whether we're running it with 10 processes or 10 million processes, we want it to scale up without any issue. So, once you have that program to work, we're going to proceed with benchmarking, and that is part 2. So, it's going to be the same as before, where you have a table of darts and processes, and for each cell, that's going to be a different runtime. And then you're going to have another table that's basically your speedups. So, say this runs in like 10 seconds, 5 seconds, 2.5 seconds, 1.25 seconds, and so on. You would denote that as a 1, 2, 4, and 8 times speedup. It's not likely going to be like that, but it might approach that the more work we give these processes. But anyway, when it comes to benchmarking, what's more important is how long it takes to throw the darts, not how long it takes to broadcast, throw the darts, and then reduce. Because we're worried about computation more than we are about how long it takes to send messages. So, once you have your pi estimating program written, you're going to have to add a little bit of stopwatch code to time how long your program's going to take. Now, we could use the time command, but that's insufficient for our purposes. We could use the C++ chrono library and get a start and stop time, but then we have to filter out, we have to contend with the fact that we have multiple processes getting all their own different times. And the chrono library can work, MPI has a few functions for us to work with already. MPI W time, if you call that, you're going to get the current time for a single process. And then if you call MPI barrier and then pass in a communicator, you're going to synchronize all of your processes across one communicator. We're going to pass an MPI com world because we're only working with the default communicator of MPI com world. So, right before you have your dart throwing code, you're going to call MPI barrier and pass an MPI com world, and then you're going to get your start time. Only after you have finished throwing all darts, you're going to then call MPI barrier again, and then get the current time again. So you have a start time and a stop time. It's the difference between those two times that you're going to get a runtime. Now, keep note of this. This is code that is being run among multiple processes. Therefore, each process is going to have its own local runtime, and they're all going to vary. So how can we get a runtime that we can say this program ran in this much time? Well, if we have, in a very simple example, 4 processes, and they all took varying times to throw their darts, we can just assume that whichever process took the longest amount of time is our runtime. So how do we transmit that information back to one process? We can do that by using the reduce function. So remember, the reduce function is a reduction operation is some operation you repeatedly apply to a reduction variable. And it turns out the max function is a perfectly valid reduction operation. So that means if we have two buffers, one for a process's local runtime and one to store the global runtime, we can then call MPI reduce to get the largest runtime among all processes. And then we can just get process 0 to print out the runtime. And it's true that we can get our benchmarks that we eventually fill out in this table. And by the way, you are welcome and encouraged to write a batch script or shell script to automate the process of benchmarking. You are going to write a slightly different command to be repeatedly called, and that is the command to run this program. It's MPI exec. Among a few other things, you also have to pass in, namely the name of the program, how many processes you want to run, and how many darts you're going to throw. So that has to do with the benchmarking. What I did not get to talk about yet is how the spy estimating program works. Imagine you got a dartboard, and behind that dartboard is a bounding square. You are throwing darts randomly across that dartboard, but some of them are going to land within that bounding square. So you're going to have darts within the dartboard, but outside the dartboard also, that's also within the square. And it's all random. The most important thing is that it's all random. After you throw all your darts, you're going to get some number of darts that made it within the dartboard out of however many darts you threw that ended up within the bounding square. So let's call that circle over square. If you calculate that ratio and then multiply it by 4, you get an estimate for the number of pi. And that estimate only gets better the more darts you throw. I should mention that you're technically not throwing darts within the dartboard, you're throwing them within that bounding square, and a proportion of them is gonna end up within the dartboard. This is a Monte Carlo simulation for how to estimate the number of pi. There are other simulations you can do. One really weird one is where you throw needles onto a plane with parallel lines spaced out, and for a specific needle length and a specific spacing, the proportion of needles that land on a parallel line is 1 over pi. So that's another way we can estimate the number pi. It's just easier to do with a dartboard because we don't have to deal with a rotated needle. Anyway, the challenge, of course, is to get all our processes to throw some number of darts. We're going to throw some number of darts, but we're going to have to broadcast that information to all of our processes, and then each process is going to calculate 1 over n. So for throwing n darts, each process is going to have to calculate for itself 1 over n darts to throw. And then each process is going to throw 1 over n darts at its own dartboard. And once that is done, we can do a reduction operation to get the total number of darts that landed within the dartboard. And once we have that done, we can calculate the number of pi. So, if you feel like you got a good handle on what to do... Oh, and by the way, the last part of this assignment is going to be the 5 questions. Where do you think the sweet spot is for thread count? It says thread count when I really mean process count. What do you think is the sweet spot for workload size? You think this is a worthwhile speed up at the number of seconds saved? And at what point did you stop seeing any speed improvements? And how would you compare this to using pthreads in OpenMP? Anyway, those 4 parts. Pi estimating program in two ways. Benchmarking with some extra code to get runtimes. It's also worth adding extra code so that process 0 writes the runtime to a file. So if you know how to do that, add that in as well. Calculating the speedups, and then answering the questions. Oh yeah, here are the deliverables. You're gonna have to post, as in addition to this assignment, 2 screenshots and 2 source code files. But really, apart from that, that's the whole project right there. So, if you feel like you got a good handle on what to do, then have at it. Oh, and same as before, you are welcome and encouraged to write a shell script that can automate all the benchmarking for you. I have instructions for that. The only other change you're gonna have to do is to replace the command to run the program with the MPI exec command. But yeah, that's it. That is the whole project right there. But if you'd like to get some guidance on how to get started, continue with the video in 3, 2, 1. Okay, new C++ project in Visual Studio. I'm gonna right-click source files and add new item. A C++ file. I'm gonna call it main.cpp. This is going to create a C++ program, but all the code is going to be in C. Let's get ready with the boilerplate code for this. So, include standard.io.h, include time.h. Because we need a random number generator for this, we need 2 libraries for this, time.h and standard library.h. There are other ways we can generate random numbers, such as the C++ random library, but that means you're gonna have to compile it as a C++ program rather than a C program. What I'm showing you here is a pure C implementation that uses the rand function. In practice, it's not really the best one because rand is not really the best random number generator out there. There are better ones out there, but we're gonna use rand because it's something that you may have encountered already. So let's just roll with that. You are welcome to use an alternate random number generator if you like. Let's zoom in really close for clarity's sake, even though I record this at a relatively high resolution, like 1440p. Okay, so this is going to be the single-threaded implementation of our PySMing program. So we can just write this as any other normal C or C++ program. So we're gonna need to seed our random number generator. So srand, that is the function to be seeded. With a seed, we are using time null to get the current time. Typically with random number generators like this, we use the current time as a seed. What we're going to do next is we're going to generate a pair of random numbers. And they are going to be within the range of -1 to +1. So I'll just do one random number as follows. I'll call it random and say, I'm going to call rand, but then I am immediately going to cast it to a double. I am then going to divide that by rand max. What's that? What that is going to do is it's going to create a random number, cast it to a double, and divide it by random max. So we're going to get, what this is going to do is create a floating point number that's basically from 0 to 1. But that is not within the range of -1 to +1. So, we have to take this quantity, as so, multiply it by 2.0, and then subtract 1.0. So now we have the following. Create a random number generator between 0 and rand max, cast it to a double, and divide by rand max to get a number from 0.0 to 1.0. Multiply it by 2, so it's 0.0 to 2.0, and subtract 1 from it, so it's -1.0 to +1.0. And now we have a random number. And now I'm gonna do it again. I just pressed Control D on my keyboard, but now we have two variables. I'm gonna call it rand x and rand y. There we go. And now I'm going to print that random coordinate. So really quick. And then we pass in rand x, comma, rand y. We're next going to use the distance formula to calculate whether our dart is within the dartboard of radius 1. So, hopefully by now you're familiar with the distance formula, but we can make a few simplifications to this by realizing one of those coordinates is 0, 0. So if we say x1, y1 is 0, 0, then it just becomes a Pythagorean theorem. So, all we gotta do is take our x and y coordinates, square both of them, add them together, and then take the square root of that. If that is less than or equal to 1, then our dart is within the dartboard. But here's the thing. On the left-hand side, that's going to be 1, but if we square both sides, we can omit the square root operation. So, with that in mind, we calculate our distance squared. Because if we square root that and it's still within the dartboard, it's still going to be less than or equal to 1. So, distance squared, and I'm going to say rand x times rand x plus rand y times rand y. If distance squared is less than or equal to 1.0, print f dart within dartboard. And now we have a program that throws a single dart. I'm going to press Control F5 to run it, just to see. Okay, we have a random set of coordinates, and it ended up within the dartboard. Press any key to continue. If I run it again, it's also within the dartboard, but we should have different coordinates now. If I run it again, different coordinates, also within the dartboard. Eventually, I should get a run in which the dart landed outside the dartboard. But why run the program repeatedly when we can just run all this code in a for loop? So I'm gonna comment out all this print code, and I'm gonna wrap everything in a for loop. And now I'm gonna cut all this code, paste it in here. And I'm gonna replace this with I'm gonna say dart %d within dartboard, and then I'm gonna add I plus 1. So let's see how many darts end up within the dartboard. Okay, are there any gaps? Yes, there are. Okay, that means some darts are landing within the dartboard, and some darts are not landing within the dartboard. Let's add a little more code. Darts to throw equals 100. And then I'm just gonna copy and paste it down here. And I'm gonna say darts within dartboard equals 0. And then I'm gonna say if distance squared is less than or equal to 1.0, I'm gonna comment out that print line, and I'm gonna replace it with darts within dartboard plus plus. There is a more shorter way for us to write that, and that is using a ternary operator. That would just collapse that whole line of code, that entire block of code, into one line of code. We're almost done with the single-threaded implementation of our Pi estimating program. All you gotta do now is this. I'm gonna say darts thrown within dartboard %d of %d, and then I'm gonna print darts within dartboard and darts to throw. There we go. Next, I'm gonna print the estimated value of pi. And that's going to be 4.0 times. I'm just gonna copy this one line of this snippet of code, paste it here, and then replace that comma with a divide sign. There we go. And then I'm gonna print out the estimated number for pi. And there we go. That's the whole program right there. So, yeah, the darts to throw is hard-coded, but there's nothing stopping us from rewriting this program so that it accepts a command line argument that tells us we can use to specify the number of darts to throw. But yeah, that's the whole program. I'm going to press Control B to build the program, and then I'm going to press Control F5 to run it. We got 70 out of 100 darts within the dartboard. That's a very bad estimate. Okay, this is 3.28, also very bad. I'm going to increase the number of darts to see if we get a better estimate. It's closer. More darts. 3.143. Oh, by the way, if you want to throw even more darts, you're gonna want to replace the ints with longs. And more to the point, the size of an int and a long turns out to be platform dependent. So there is an alternate set of data types you can use that are guaranteed to be 32-bit and 64-bit. I'll leave it to you to look that up on your own. But I am just gonna, for our purposes, we're gonna assume an int in this context is 32 bits long and a long is 64 bits long, even though that's not always gonna be the case. So you can either replace these ints with longs or a integer data type that is guaranteed to be 64 bits long. That is if you want to throw even more darts than what a 32-bit integer can handle. You don't have to do that, but you can. Alright, there we go. We have 785,000 darts out of 1,000,000. We have an estimated value of pi to be that much. So our program works. So this is our single-threaded pi estimating program. And just to show that this works on a Linux operating system, I'm gonna create a new file. I'm gonna call it pi.c. No, vi, that is the built-in text editor, pi.c. This is the only way I know how to make new files in the command prompt here. Okay, so now I have my text file. I'm just gonna close that and paste in all my code. So now all this code should work now. With this terminal open, and it's going to be right-click in the blank space and then open in terminal. That opens the terminal in the current location in Linux's equivalent of File Explorer. If I type in ls, I can see we have the pi program source code. If I type in gcc-o pi.c, that's going to compile my program. And if I do /pi, I get the same result as I did on the Windows machine. Oh, by the way, if your system has the Windows subsystem for Linux, if you have that on your system, you're basically bypassing all the virtualization needed to run a virtual machine. So if you have WSL, you're one step ahead you're further ahead in the game, basically. But you are going to be using all the same commands as you would on a Linux terminal, just on Windows. So you can do this in the virtual machine, you can do this in WSL, you can do this on Windows. Doesn't matter what platform or means you're able to run this, as long as you have MPI installed in any way, shape, or form, you're able, and you can compile it, and you can do MPI exec, you're able to do the whole project. Okay, so now we have a single-threaded pi estimating program. Let's go back to the Windows machine real quick, because now we are going to have to parallelize this to work with MPI. Problem. Visual Studio has no idea what MPI is. So, let me just go in here, click Project, Properties, go to C/C++, Additional Include Directories. Click the drop-down box, click Edit, click the blank space, click the little ... button over here, and navigate to where you have the following folder: Program Files x86, Microsoft SDKs, MPI, Include folder, Select folder. Click OK, click Apply. We're not done yet. There is another thing we have to add, and that is additional library directories. Take note of whether your project is x86 or x64. Mine is x86, so I'm gonna take a mental note of that and go back to that directory with the MPI folder under the SDKs folder. So click the blank space, click the little ... button, go back to where Files x86 is. By default, that's going to be the location of the API, unless you've changed it. So go to your C drive, unless it's somewhere else other than the C drive. Go to Microsoft SDKs, go to MPI, and go to Library. Enter that, and because my project was an x86 project, I select the x86 folder. If you are running an x64 project, you want the other folder instead, x64. Select folder, click OK, click Apply. We're almost done. We have additional dependencies. Click the drop-down, click Edit, and then in the text box, type in msmpi.lib. These instructions are specific for a Visual Studio project on Windows. And from what I understand, Visual Studio is Windows only. If you are on Visual Studio Code, the process is going to be different. But if you are on a Unix machine, and Macintosh systems are Unix machines, do the following sanity check before you proceed at all. Type in MPICC. If you get GCC fatal error no input files, or if you do MPICXX and you get the same error, that means you have the compiler. It's possible that you have the compiler, but not the header file. Turns out you need both the header file and the compiler to get MPI programs to work. So make sure you have both. And if you don't, find a computer on which you can run your programs. I know for a fact that my Ubuntu virtual machine has MPI installed on it already. I know because I underwent the install process a long time ago. And the fact that it says GCC fatal error no input files means, hey, it's installed already. Okay, back to Windows. I said back to Windows. Okay, so now our program is ready. Let's add the necessary boilerplate code. And that is int my rank and com size. So those are going to be our two variables that we're gonna need. After that, we can call MPI init and then pass in null. There we go. MPI com size, and we're gonna be working with the default communicator of MPI com world, and then pass in the address of com size, and then MPI com rank, MPI com world, and then at the address of my rank. There we go. Now we know. Now each process is gonna know where it is in the communicator. So now, if we run this program by pressing Ctrl F5, it's gonna get blocked by my firewall. I'm gonna allow access, and realize that this is not how you run a MPI program. I've shown you how to navigate to where your source code file is, and more importantly, the executable. But there is another way. Open in terminal. And we have PowerShell here. So if I type ls, I can see 3 files in here. And one of them is the debug folder. If I type, I don't have a good way to zoom in here. If I type cd debug and type ls again, hey, there's an executable file right there. See? Over here. Down here. See? If I press Ctrl-Shift-B, that's going to build the program. Now, if I type MPI exec -n, and I'm gonna run it with 10 processes, and then I'm gonna pass in the file, the executable name, CSE-5250 _SPR2026 _PI.exe. If I type that in, I'm gonna get some issues because I think I forgot a few other things. Oops. I forgot to add MPI finalize. Let's fix that up really quick. Press Ctrl-Shift-B to recompile the program. Yeah, it broke because it didn't finalize properly. So clear, and I'm gonna type in that command again. So now, every process is running a copy of the original program. We don't want that. We want this program to divide the number of darts among however many processes we have. Okay. So we're gonna have to make a couple of modifications. Okay, so we have our darts to throw. But that's not enough anymore. We know how many darts to throw overall, but we have to divide that by the com size to get the number of darts each process gets to throw. So, int local darts to throw, and I'm gonna divide darts to throw by the com size. That is not enough though, because if we ran this program with a quantity of processes that does not evenly divide the number of darts, we're going to lose some darts. It's not a lot. It's not going to be a lot in the long run, but we want to make sure this runs no matter what number of processes we have or the number of darts to throw. We want it to work. We want it to scale no matter what. So that's just going to be an easy fix. If we have the last process, we can just add those missing darts back. So let me just comment this code. And so every process is going to run its code with the same number of darts, except for the last one. That's not totally load balanced, but in the long run, it doesn't really affect it. It's going to be roughly balanced, and that's going to be okay for our purposes. Okay. If this is the last process, and we can know this is the last process if we say my rank plus 1 equals com size. It also works to say my rank equals com size minus 1. Doesn't really matter which one you do. But if this is the last process, it adjusts its darts to throw by adding the remainder of darts to throw divided by com size. So I'm just gonna copy this line of code, paste it in here, turn that into an increment operation, and replace that slash with a %. Now we are adding the remainder of darts to throw over com size. That's darts to throw mod com size. And now every dart has been accounted for. Let's add a little bit of extra code just to make sure this thing is working. Process %d will now throw %d darts \n, and then we're gonna pass in my rank and local darts to throw. There we go. Oh yeah, we have to adjust the for loop here because it's not going to be the global darts to throw, it's going to be the local darts to throw. And since we have that calculated for every process, all we gotta do is just adjust the for loop, and that's it. One other thing that may be necessary, I added this just to be sure that this will work, and that is the following. In my experience, I've had every process start with the same seed. To guarantee that's not going to be the case, I just simply add my rank to the seed, and there we go. Again, this is just to guarantee that every process gets a unique seed. Because if every process had the same seed, they're gonna throw the same darts at all the same locations. Because this is deterministic. If you use the same seed, we're gonna get the same darts being thrown. Like how a Minecraft seed will give you the same world generation. If you type the same seed, so like in a Minecraft seed, if you have some sequence of characters that you use as a seed, if you type that into Minecraft, you can generate the same world, assuming that it's gonna be, assuming it is the same version, because Minecraft world generation has changed a lot over the years, so yeah. So anyway, this adjustment is to guarantee that every process has a unique seed. This is just the easiest way to do that. Just add my rank to srand time null. And now we should have a parallelized dart throwing program. So I'm gonna press Ctrl-Shift-B to rebuild the program. I'm gonna clear this, and I'm gonna run the command MPI exec again. So now each process is going to throw. Actually, no. I need to make a few more adjustments. Darts within dartboard and darts to throw. This is the global darts to throw. I do not want that. I want the local darts to throw. So each process is gonna say that. And also, one modification we also need to do is this. I'm gonna change darts within dartboard to local darts within dartboard, because we're gonna also have a global darts within dartboard. We're not gonna use that yet. So we have a local darts to throw and a local darts within dartboard. I'm gonna copy that variable and replace darts within dartboard with local darts within dartboard, and then there we go. I've replaced every instance of local darts within dartboard. Every instance of darts within dartboard has been replaced with local darts within dartboard. So now, if you look here, the calculation is incorrect actually. So if I run this program now, if I rebuild the program and run it, now every process is calculating its own estimate for pi. But what we eventually need to do is to do a reduce operation so that process 0 gets the total number of darts and uses that to calculate the estimated value of pi. So we have our local darts within dartboard, but we now need to get the global darts within dartboard. Okay. That function is MPI reduce. We must pass in the global darts within dartboard, which I just named as darts within dartboard. I must pass in local darts within dartboard. I'm gonna continue on the next line because it's gonna be long if I don't. We have one value being brought. We have one value being sent. It is a data type MPI int. We are performing an operation of MPI sum. Process 0 is gonna hold the reduction variable, and we're only gonna do this within the default communicator MPI com world. There we go. We're almost done. We're almost done. We're almost done. Okay. The last thing we have to do is to print the estimate for pi, and I'm gonna have process 0 do that. For process 0, calculate the estimated value of pi. So, if my rank equals 0, I'm gonna move all this code within this block, and I'm gonna replace all the local darts within dartboard and local darts to throw with their global versions. Okay, so let's step through what we have now. We are using MPI to divide the number of darts to throw among all our processes. Then each process is going to throw its own set of darts at its own dartboard. We're going to do a reduce operation to get the global number of darts thrown, and process 0, and only process 0, is going to print the estimated value for pi. Alright, let's see this in action. I'm going to press Ctrl-Shift-B to build the program, and I'm going to clear the console here, and then I'm going to run MPI exec. There we go. Okay, total darts within dartboard. Okay, there might be a few issues here, and that is, I think... Okay, I found it. Hold on. I may have to do some debugging first. Okay, let's see. Darts within dartboard. Okay, I did it incorrectly. I swapped the two variables. So this is wrong. It should be... should be... what to send and where it's going to. So source and then destination. I had it backwards, so I was doing it all wrong. Everything else was being calculated properly, where we had 1 million darts being thrown amongst 10 processes, so each process was throwing 100,000 darts. So that was correct. I had the source and destination mixed up, and that's why the program was not working as intended. Rebuild, and clear, and run the program again. I apologize if this zoom level is way too small though. I'm sure there's probably a way to make it bigger, but yeah. Okay, there we go, there we go, there we go, there we go, there we go. So now we have an estimate for pi. So every process drew some number of darts. We do a reduce operation to get the number of darts thrown among all processes. We got an estimated value for pi. If I did this with 11 processes, then what we should find is there's going to be one process that's gonna throw at least one more dart than everyone else. And that's because 1 million divided by 11 produces a non-zero remainder. We have to add that back to the last process. But it still works. Nice. We have to make a change to this program. And that is this. We have to modify the executable so it accepts command line arguments. So int argc character star argv square brackets. And that is because we want to get the number of darts to throw as a command line argument. So for us to do that, let's replace this with string to long strtol argv 1 comma null comma 10. There we go. So now we can run the program with a number of darts that is arbitrary. Let's try it out. So I'm gonna run this again, and I did not build it yet. So I'm gonna press Ctrl Shift B to rebuild the program. And now if I run this program again, I got an error because I did not specify the number of darts to throw. So abort and clear. Run it again. I'm gonna run it with 11 processes and whoops. No, I do not want to debug like that. Hold it. I'm gonna run it with this many darts. If I press enter, it's gonna roughly divide the number of darts among all processes. Darts thrown within dartboard is going to be this proportion, and we get an estimate for the number of pi. It works! So now this program is going to work with any number of processes we want and any number of darts we want. So we've just completed the program itself. The only thing left is benchmarking. Okay, so now we are gonna have to make a few more tweaks to our program. We need those barriers. Okay, so before we throw any darts, synchronize before throwing darts, MPI barrier, MPI com roll, and start time equals MPI W time. Okay, so this is not going to work because I did not define the start time variable. I need to define those variables right now. So I'm just gonna define them down here. Alright, so double start time, stop time, local runtime, and global max runtime. So now we have our start time and stop time. Technically, these are local start time and local stop time. So now we have a barrier. We're gonna copy that code and paste it down here. Synchronize after throwing darts, and this is our stop time. So now we have a start time and a stop time. We want to then do another reduce operation. it's gonna be another reduce operation. So I can just cheat by copying, pasting that reduce function up there. But now I need to swap the variables. So the source is going to be local runtime, and the destination is going to be global runtime. I still need to do one more thing, and that is local runtime equals stop time minus start time. Okay, did that work? Did I miss anything? Local runtime is undefined. Well, that's embarrassing. I misspelled local runtime. Let's fix that real quick. Okay, do that, and there we go. Control-Shift-B, rebuild the program. So now we have the ability to not only throw the darts, any number of darts, and any number of processes, we can also print out the runtime. So I'm just gonna rebuild the program again. Clear. And there we go. It took, well, that's not right. Did I swap the source and destination again? Or what? Hold on. I did the wrong things. This reduce operation is not passing an int, it's passing a double. So MPI double. And this is not a reduction operation of sum, it's a reduction operation of max. So MPI max. Rebuild. Okay, rebuild, clear, and run it again. And it took about half a second to run. No, less than half a second. That is like, what is that? 57 milliseconds to run. So this time is in seconds. If I tried to run this program with even more darts, it might start to overflow if I make it too big. So I'm just gonna forcibly close that. And what I'm actually gonna do is I'm gonna swap the darts to throw to longs. So I'm gonna convert all of these to longs just so I can throw even more darts. If I change these data types from ints to longs, it means I have to change the reduce operation from MPI sum to MPI. No, it says sum, but it has to be MPI long. I'm assuming that this is the right version. Actually, no, I have to double check this. Okay, so I'm just gonna run with MPI long, and if that does not work, then I'm gonna have to swap it out for the explicit data type of MPI int 64. Well, technically MPI int 64t. So that's how you would do it with the explicit data type sizes. So I'm just gonna run with long because, well, this is long already. Control-Shift-B to rebuild, and I'm gonna run it again with that many I think it's slow because that's just a lot of darts. So I'm gonna run that again, but with maybe it is a lot. Okay, there we go. That took 5 seconds to draw all the darts. So the reason why it took so long is because there was just a lot of darts to throw. But yeah, now we are ready for benchmarking. At this point, I highly recommend you add additional code to make your program write down the runtimes. If you do that, you're gonna make your task of benchmarking easier. I'm not gonna show you how to do that right now. I assume you know how to do that, or you know how to look up how to do that for yourself. For now, I am just gonna take this code and show that it works on a Unix machine. Okay, so back in my Unix machine, I have the program here. I'm gonna have to clear and recompile the program with MPI. That's the start of the command, and yeah, the command is long and I have to look it up each time. But it is going to be MPI-G -wall -o. I called it pi, and the source code file is pi.c. If I do that, I am going to get some warnings about mismatched data types. I am going to go ahead and fix these things up really quick, because if I don't, it might cause a few issues. Okay, so on line 30, I had %d when that should be %ld. And maybe I have to change these out to long int. See what I mean about it's hard to know what size words are. Yeah, maybe it would have been a better idea to use int 64t instead of whatever this is supposed to be. But that is just a simple change of data type. I'm gonna leave that to you to figure out on your own. But this is what I mean by it's sometimes hard to know whether sometimes it's hard to know what size your data types are. So yeah, I just have to contend with the consequences of my actions and tell you that so you don't have to repeat my own mistakes. And then on line 74, I have a similar issue. LD or %LD. Just want to make sure that this is going to work. Yeah, but at least you get to see all my mistakes. If I recompile this now, will I get the same errors? Well, they weren't errors, they were warnings. Okay, it worked. A little bit of cleanup later, and now the program should work. Okay, let's run the program using MPI exec. So I named the program pi. So MPI exec -n. I'm gonna run it with 6 processes because that's the max on my virtual machine. And I'm gonna type /pi. Okay, so something went wrong. And I think I know what went wrong. I forgot to specify the number of darts. Oops! Let's do that again, but let's do it with a billion darts. This might take some time. Okay, we have the number of darts, and then it calculated the number for pi, and it took 3 seconds. Let's do something a little bit smaller. Let's do 10 million darts across 6 processes. Press enter. It took about 0.048 seconds. If I did this with one process, I should expect this to take longer. And it did. Okay, it's working. Now we have the whole thing working. Okay, now comes the matter of how do we automatically benchmark this thing. Well, we have the commands here already. So if we were go back to our discussion about the batch file. Let's start with the batch file first. Okay, so back in Windows, I am going to right-click the solution here and open in File Explorer. So now I go to the debug folder, and that's my executable. So now I have to write a batch file. I'm just gonna create a new file and type benchmark.bat. If you change the file name extension, it might become unusable. Are you sure? Yes, I am sure. Right-click, and I'm gonna edit this as a text file, and the most basic code for our purposes is as follows: 4%/L %%I in 1,1,30. So this is gonna run the command 30 times. Do it's not gonna be enough to type in the executable name. I am, by the way, referring to the instructions for the batch file here. So this was posted a while ago for the MPI, not MPI, the OpenMP benchmarking. This is the minimum you need to do. But if you want to be more smart about it, you can turn it into this. It's just that we do need to do some rearranging because the number of threads and the number of processes have to go in different places because the command is different. That command is MPI exec -n. I'm gonna do this with 4 processes, and I'm gonna type in the name of the executable, that is CSE-5250.SPR2026 _PI.exe, and then I'm gonna type in 1 million. So this is gonna run a single benchmark 30 times, 4 processes, 1 million darts. If I run it by double-clicking the batch file, actually no, that ran it way too fast. I have to actually type in CMD in the address bar, and now we have to enter the name of the batch file, which is benchmark.bat. It's not working. Okay, let me debug this really quick. Okay, I found the error. I had a parenthesis that was paired with a curly bracket. That is incorrect. Alright, let's see if we can get this thing to work now. If I... Okay, now it's working, now it's working, now it's working. Now it just ran the whole program 30 times. Okay. For ease of benchmarking, it might be a good idea to go back into code and silence all processes that isn't process 0. So, in the code, I have several printf statements. I'm just gonna comment all of them out. So MPI reduce And then I'm just gonna print another new line after that. So what I've done here is only process 0 is allowed to talk. And what it does, it's gonna print 3 lines of code. It's gonna print 3 lines and then print a new line after that. So there we go. Save that. Rebuild. And if I go to command prompt again, to open the command prompt, just type in CMD in the address bar. And there we go. We have our command prompt. And to run the benchmark bat script, we type in benchmark.bat. And there we go. We have automated benchmarks. Okay, it would, if you can write the times to a file, you will save yourself a lot of headache. Oh, and by the way, if you want to adapt this code so that it works with looping through all of your process counts and Dart counts, what we need to do is modify the batch file as follows. Okay, so let's step through this triply nested for loop once more. The outermost for loop steps through our quantities of darts. I'm just showing 10,000, 100,000, and 1 million, but in practice you would choose larger numbers than that. I am only going to do thread counts 1, 2, 4, 8, and 16, but if you have a more powerful CPU, feel free to add more processes to that. And I'm only running each benchmark, running each combination of Dart count and process count 10 times. And this is the command you run. So %% is the number of processes, %s is the number of darts. And the equivalent code for a Unix shell script would have you replace this command with an equivalently rearranged it would be the equivalent line of code here, except it's going to be $S in quotes and $T in quotes, but the $T must come before the name of the executable, and $S must follow the name of the executable. So yeah, you would just replace this line here with the appropriate equivalent MPI exec command, and then you have your whole benchmark in one file that you can just run and do. And that's it. That's all your benchmarking done. Assuming you have code that can write all of this to a file. Again, I'm just giving you the minimum things to do. I'm just going to be giving you the minimum information for you to get started and then just tinker with yourself. So if I run this program now, it's going to do auto benchmarking. Now, what would be also advantageous is to have it also print out the number of darts and processes run, but that might not necessarily be needed here. If you have your program print out all your benchmarks, all to separate files. But yeah, that is the entirety of your benchmarking project. So yeah, that's gonna be it. So if you have any questions, let me know. And yeah, that's gonna be it for the entire course. So thank you for sticking with me throughout this whole semester, and until again.